Dragi membri ai comunității UBB, dragi prieteni virtuali, bine v-am regăsit la o nouă prezentare din seria de conferințe organizate în cadrul programului Studium Generale al Institutului Star UBB. Mai întâi doresc să vă reamintesc că Studium Generale reprezintă o serie de conferințe săptămânale în timpul anului academic, ținute de personalități ale universității sau invitate, care tratează o temă a propriei discipline în dialog cu alți membri ai universității și nu numai. Tema conferinței de astăzi este Analyzing Complex Cause-Effect Models in the Social Sciences și va fi prezentată în engleză de către domnul Marco Sarstedt, profesor la Ludwig Maximilian University Munich din Germania, iar în cele ce urmează vom continua prezentarea în engleză. So, Marco Sarstedt is one of the world's most influential researchers and will be awarded next week the title of Doctor Honoris Causa of Babeş-Bolyai University. He is also one of the most important and famous experts in partial least square structural equation modeling, PLS, SEM. Over the last decade, Marco Sarstedt has made significant contributions to the methodological development and popularization of PLS-SEM among researchers around the world in the most diverse fields, especially in the social sciences. His papers were published in prestigious international journals such as Nature Human Behavior, Journal of Marketing Research, Journal of the Academy of Marketing Science, and others alike. The international influence and impact brought Marco Sarstedt the status of highly cited researcher in 2018, a status he maintained since then. Currently, his published papers count for over 100,000 citations according to Google Scholar. Before giving the floor to Professor Sarstedt, I would like to remind you that you are welcome to ask questions live on the chat of the YouTube channel broadcasted by Studium Generale. I will address these questions at the end of the presentation. Dear Professor Sarstedt, thank you very much for accepting our invitation. It is a great honor to have you as a guest speaker at our seminar. We are very much looking forward to your presentation.
Wow, thank you very much for the kind introduction. I'm really honored to be here with you today and talk a bit about the topic that Gabriele already outlined a bit, namely partial least squares. So I used the Romanian title here, but I guess I'd rather present in English because my Romanian is not that far developed, not at all. So I'm going to be talking a bit about analyzing cause-effect models in the social sciences, and I'm going to put special emphasis on partially squares, structure equation modeling, also talking a bit about as to why this method is, in my point of view, so important for the social sciences in general. So a few words about myself. Well, I've already been introduced, so I'll keep that rather short. As already mentioned, a professor of marketing actually at the LMU in Munich, also an adjunct research professor at Babeş-Bolyai University, and I'm also active in like professional bodies related to marketing, like the German Marketing Association, which is like a professional association for marketing practitioners. So this tells you a bit about my research, which is also very practitioner oriented, not necessarily in the research methods field where my mainstay of research is, but also in consumer behavior, where I deal with choice anomalies, biases in consumer behavior, and irrationalities, and how to actually tackle them in various contexts. But this is not the topic of today's session. Today, we're going to be talking about what you see here in the middle, namely partially squares structure equation modeling or structure equation modeling in general. So first off, today's menu is giving you a broad introduction of what SEM actually is, and as this is a studium generale, I thought I would offer like a bit of a broader overview of what that actually is and what it's useful for, assuming that most of you that are currently listening online are not aware of structure equation modeling and the details related to this type of methods. Yeah, so I'm not going to talk too much about the technical details, but more give you a broad overview of, okay, what is it useful for, what is PLS all about, what other estimators could we use, and what are the basic steps for conducting such an analysis. And I'll try to give you some references and recommended readings if you find that this could be of interest to you. So let's kick things off by talking a bit about what structure equation modeling is. And like the general description of structure equation modeling is that it's a class of procedures. So it's not like a single procedure, but it's a class of procedures used for analyzing complex cause-effect models. And these cause-effect models comprise latent variables, also referred to as constructs, and indicators. So this already tells you a bit about the use case for structure equation modeling. It's all about modeling unobservable concepts. Yeah, so oftentimes the concepts that we are interested in the social sciences, and especially in my field as marketing, these concepts are unobservable. Yeah, meaning that we cannot measure them directly. Yeah, so they carry labels such as customer satisfaction, customer loyalty, brand authenticity, or choice difficulty, something like this. Yeah, so they all have something in common, namely that there's not like a universal description what they actually are. So they are abstract, meaning people can assign different meanings to these concepts. Because of that, measuring them is not that easy. So we can't ask a single question asking about satisfaction. I mean, we can do that, but it's probably not a very good idea, because when you ask people about their satisfaction, for example, with a service or a product or a company, they might think about different aspects of the satisfaction. So what do? We use multiple items, which are generally conceived as reflecting some trait, yes, some unobservable trait. You can see such a set of items here in this chart at the right-hand side. This is a structure equation modeling, and these ellipses, they actually represent the constructs. So constructs are the entities that we use to represent these abstract concepts in a statistical model. And these constructs are linked to indicators, and these are the boxes here. So for example, you see a construct which is labeled competence down here. And competence, well, it's the perceived competence of a company. This is an abstract concept because, well, what's competence? Well, there are multiple meanings that people can assign to this concept. And it is measured using 3 indicators. These indicators in this specific example actually stem from survey data, but you can also gather indicators from all other data sources like secondary data, databases, grab them off the internet, whatever, you name it. So, but here we are actually looking into survey data, and we see 3 types of indicators which relate to statements which people could agree or disagree to. So for example, this company, let's say, as an example, Apple. Yeah, Apple is recognized worldwide, and people could agree or disagree to the statement on, say, 7-point scale. Apple is a top competitor in its market. That could be a second item, and then a third item, Apple performs at a premium level. So we use these 3 items as reflections of the underlying construct, the competence. So here you can see that the relationship goes from the construct to the indicators, because we conceive these items as being reflections of something that actually exists. Yeah, so we have a certain view of a company in terms of its competence, in this case, Apple, and asking our respondents these 3 questions brings this assessment, this perceived competence to the fore. Because all these 3 indicators are measuring the same thing, supposedly, and hopefully they do, yeah, we would expect high correlations among them. This is an important trait because these correlations are actually being used as input for the analysis and particularly for the validation of these models. You also see other types of settings here. For example, overall satisfaction. Overall satisfaction is measured with a single item. Yeah, this is actually something that you would typically avoid in these types of latent variable models or structure equation models, simply because the concepts that we are measuring are typically too complex to being measured with a single item. Here, I put this in as a use case to give you a bit of an impression of that, the fact that this could also be done, right? We also have a different set of constructs up here, for example, CSR, attractiveness, quality, and performance. And you might notice here that the relationships go into a different direction. So it's not like with competence where the arrows go from the construct to the indicators. Here we actually say that the indicators are jointly forming the construct. So this is simply a different type of measurements or construct operationalization, as we call it. And this is referred to as a formative approach. So you can actually see here that such a structure equation model has different elements. We look into the relationships between constructs and indicators, and obviously between the constructs. These relationships between the constructs, represented by single-headed arrows, are typically linked to hypotheses that we formulate. So for example, we as researchers could hypothesize based on theory and logic that CSR, which stands for corporate social responsibility, has a positive effect on the likability of a company. We could also hypothesize, for example, that CSR has a positive effect on the perceived competence of a company, and that these two dimensions then impact customer satisfaction and customer loyalty. So you can see these structure equation models have numerous layers of constructs being linked to each other so that we can establish some type of causal chain from the left-hand side, for example, starting from CSR, to the very right-hand side, ending in our example here with customer loyalty. This is one important feature of structure equation models, that it allows for estimating fairly complex models in a causal chain-like manner. However, the main reason why structure equation modeling has actually been developed lies in the fact that we want to gain a bit of a more precise measurement. Because if we use multiple items to measure a construct, for example, competence, well, what do? In standard applications of, say, a regression analysis, we would simply take these three items that I mentioned before, recognized worldwide, top competitor in its market, and performance at a premium level, and simply average them. With this average, we could run a simple regression. Well, that's commonly done, but it's not a very good idea. Because by simply averaging these items, you're assigning the same weight to each of these indicators. The problem is that it's very unreasonable to assume that each of these indicators has the same importance for customers' perception of a company's competence. And another reason is that each of these indicators has a certain degree of measurement error. This measurement error simply occurs because people might be in a bad mood, might be in a very good mood, and because of this specific mood, which can be randomly high or low, they answer these questions, these Likert type items, differently. So this error might not be systematic, but it can be random, and this random error generates some type of white noise that makes it difficult to extract the true effects in such a model. But because of this measurement error, researchers have developed latent variable approaches which allow for, at least to some degree, accounting for this measurement error. So they kind of correct these estimates, taking into account this measurement error. This is the primary aim, actually, of structure equation model. Correcting for measurement error and analyzing complex relationships among multiple constructs. So I already referred to some terminologies here. I refer to what we call the structure model. The structure model defines the relationships between the latent variables, the constructs. We use these terms, by the way, interchangeably. So either we refer to a construct or a latent variable, same thing, right? And these relationships that we formulate in the structure model are typically linked to our hypotheses that we derive based on theory and logic. We then use empirical data to test these relationships, and we get typically standardized estimates, which corresponds to the betas in a regression. So for example, we would, after some iterations of an algorithm, regress y3 as a dependent variable on y1 and y2. And the result of this regression gives us two beta coefficients, which we refer to path coefficients, which are standardized, meaning that they typically vary between -1 and +1, and with higher values denoting stronger positive or negative relationship, and it's close to 0, well, it's actually a null relationship. Second important element of such a structure equation model are the measurement models. And the measurement models define the relationship between each construct and the indicator. So they actually tell the researcher and the program that's actually used for estimating this, how each of the construct is being operationalized, so which indicators are being used. We distinguish here between a reflective and formative measurement model. I was briefly referring to that before. So in a reflective measurement model, the indicators are seen as reflections of the underlying construct. The theory says that this underlying construct actually causes the correlation between the items. Well, I'm a bit cautious with the term causes because, I mean, obviously the construct doesn't have any causal power, but that's the best way to describe it, really. So we see some correlations between, say, x11, x12, x13, and this correlation pattern that we see is actually caused by y1. What we are getting here is our estimates telling us a bit about the strengths of this relationship in the form of so-called outer loadings, which are simply the bivariate correlations between the construct and an indicator. Something that you will know if you have ever worked with a factor analysis, same thing that you're getting when, for example, running an exploratory factor analysis, the factor loadings, same thing here. Yeah, simply the bivariate correlation between the factor, in this case, construct, and each of the indicators. At the lower side here, you see y2, and y2 is measured formatively, meaning the indicators are seen as kind of causes of the construct. Again, the indicators don't have any causal powers, but you can think about them as being antecedents. So they jointly define the construct. In a simple sense, this could be an index, like, for example, a company investing into different communicative measures. Yeah, so they spend a certain budget on online advertising, in print advertising, linear TV advertising, radio advertising. Yeah, so you take these items and form an index of advertising expenditures. Yeah, but in other cases, you could also use such an index to measure an unobservable concept, such as, for example, satisfaction with this talk here. And you could use indicators such as, well, perceived competence of the speaker, quality of the slides, competence in answering questions, whatever. You know? In this case, we also get a set of correlations, but these are different from the ones in the reflective measurement models because they are partial correlations telling us something about the impact, the relationship between each indicator and the construct, given that there are also other indicators in the same measurement model. Yeah, so we get here the beta weight, which basically results from a regression of y2 on the corresponding indicators x21, x22, and x23. We can also distinguish between different types of constructs, something that are omitted, exogenous and endogenous. Endogenous constructs are those that are being explained in such a model, such as y3 here, and exogenous are those constructs that explain something like y1 and y2. If a construct is both exogenous and endogenous because, well, it has an arrow pointing at it, which makes it endogenous, and then some arrows pointing out of it, which makes it exogenous, well, we refer to this construct as endogenous as default. So if you run such a structure equation modeling analysis, you basically run through a series of steps which are outlined here. And it doesn't really matter which type of approach you're using. These steps are practically always the same. So first off, you need to specify the structure model, which is typically strongly tied to your research field. Yeah, obviously, you have some model in mind, maybe an existing model which you want to transfer into a different context or extend. This is what you do then. Well, and I'm going to be talking briefly about that in a second. The second step is then to specify the measurement models. Sometimes the most challenging step, because you need to actually find suitable measures for each of the constructs that you're using in your model. Then you collect data, examine it, get rid of outliers, treat missing values, for example. So those things that you would do with any statistical analysis, so that's no different here in PLS than in any other statistical analysis. You then estimate the model using some type of algorithm. There are obviously different types of methods that we could use. We're going to be talking about two types of methods, which we can briefly distinguish. But in each of these subgroups, you have numerous other estimators. So literally dozens, if not even hundreds of different estimators that you could use, all with their specific properties and use cases. Then we assess the quality of the measurement models. The idea is to ensure that the measures that you're using are actually valid and reliable, because only if they are valid and reliable, you can actually interpret whatever comes out of these measures, yes, meaning the structure model. So otherwise, it's kind of a garbage in, garbage out model. Yeah? So you're using a not very qualitative or good, like valid, or let's say, okay, let's put that differently. You use an unreliable measure to measure, for example, perceived competence. And if you're doing that, obviously, it makes very little sense to look into the relationships from competence to, for example, satisfaction or loyalty. That's why the measurement model assessment precedes the structure model assessment. Let's go briefly through these steps. And briefly, I really mean briefly, yeah, because typically we spend in our workshops about 4 days discussing all these steps and a series of additional analyses. So obviously that's very challenging in 1 hour, but I'll just try to give you like a 30,000 feet overview of what can be done here. So in the first step, we specify the structure model. And as I said before, the structure model refers to the hypothesis that you specify. The relationship that you test are basically empirical manifestations of the hypothesis that you formulate based on theory and logic. So the first thing that you do is first off determine the constructs of interest. And determining the construct of interest basically means having a rough understanding of what they actually are. So you have a bit of like a working definition. The model that you saw earlier, the complex one on the first slide, that's actually a model of reputation. You didn't see reputation on there, but why is this? Well, because we define reputation as a two-dimensional construct with the 2 dimensions, competence and likability. So competence is more like the cognitive perception of a company, whereas likability is more like the effective perception of a company, whether you like it. Right? You can judge any company on these 2 dimensions, and jointly these 2 dimensions define the corporate reputation. So when you want to measure or set up a model comprising corporate reputation, you need to have some type of working definition for this. Right? So a rough understanding, because this is what you need to specify the model. You also need to distinguish exogenous and endogenous constructs, identify the relationships among them. Obviously, reality is extremely complex, right? So it's not the aim of modeling to fully map, to fully represent every aspect of reality. It's practically impossible, right? Because that's what students oftentimes say, well, isn't this model too simple, right? Isn't it too simplified? Yeah, that might be true, but a simplified model is not a bad thing. Yeah, in a simplified model, you're actually trying to identify salient relationships that exist in reality. The idea is to have like what we call a parsimonious model. So a model which is not too complex so that it generalizes well to different settings. Now, for example, if you set up a model for corporate reputation of Romanian companies, yeah, you would actually tie this to your specific perception of the Romanian market. Right? But does this model then generalize to other countries, yeah, like Germany, US, whatever, right? Yeah, not necessarily, but the odds that this actually will generalize to other contexts actually increases if you have a parsimonious model, so a not too complex model. Obviously, you can argue what a not too complex model is. So how many constructs do we need? One of the advantages of the method, which we'll be discussing in a bit more detail, namely PLS, is that it allows for estimating models of very high complexity. So if you want to estimate a complex model, you can do it, right? But with other approaches, like the more like classical structural equation modeling estimators, this is hardly feasible. So this is a simple path model which we could hypothesize. Yeah, the path model is actually a diagram which connects these different latent variables, something that we could also refer to as a structural equation model. But in a structural equation model, we typically also add the indicative. Yeah, but essentially it's the same thing. So as I mentioned before, we distinguish between exogenous and endogenous constructs. Exo meaning from the outside, meaning that the model the construct explains something. And then we have endogenous constructs, which are being explained in the model. You can see here that satisfaction acts both as an endogenous and an exogenous construct. Well, it's endogenous because it is being explained by reputation, and it is exogenous because it explains loyalty. We would consider this construct as endogenous by default. In the path model, we would then hypothesize these relationships and also the sign of these relationships, and then use obviously empirical data to test whether we can find any support for these hypotheses. An important thing to keep in mind is that structural equation modeling is simply an analysis of correlations and covariance. Yeah, so strictly speaking, we cannot verify any causality here. This is why I don't like this term cause-effect models too much, even though I used it before. I guess I did, yeah? Because there's actually nothing truly causal here. However, we could obviously use these models also for causal analysis, for example, in experimental designs, by introducing interventions and then see how these relationships actually change as a result of the interventions. For example, showing some type of advertisement to the respondents or lowering their serotonin levels to cognitively impair them, as we did in one of our studies. Yeah, but at the end of the day, you got to keep in mind that we get results, whether we draw the arrow from left to right or right to left. If we have a simple model like this one down here, we'll actually get virtually the same results if you draw the model from reputation to satisfaction or satisfaction to reputation. Nevertheless, you can certainly interpret such models at least partially causal with some like limitations. Yeah, because if you have good data, high quality data, maybe even longitudinal data, and if you have a strong theory supporting these relationships, it's very reasonable to assume that there's a causal relationship here. Yeah, but if you're like a purist, in the strictest sense, this wouldn't cut it either, right? But I mean, in most of social science, at least, we would expect that if you have good data, if you have a strong theory supporting these relationships, and also some intuition which tells you, okay, this is likely to be true, yeah, you can actually probably make some type of causal statements, but maybe regarding the direction and the significance of the relationships, but certainly not when it comes to the strengths of these relationships. Yeah. So I'm sure you're aware of many such examples where people would infer from correlations to causality. A nice one is one here, which has actually been published in a paper 10 years ago, where the researchers looked into the relationship between chocolate consumption and the number of Nobel laureates per 10 million population. And they argued actually if people consume more chocolate, they have a higher cognitive capability because there's a higher dopamine production, and if this happens, they're just more productive, right? And then they end up winning more Nobel Prize, which is obviously rubbish, yeah. Because there's maybe some background variable here explaining this relationship. So we always have to be aware of the fact that there are confounders, that there could be kind of phantom variables causing correlation. In this case, maybe actually the industrial development of the countries, which is actually, on the one hand, impacting the chocolate consumption. So if you have lots of money on your hands, yeah, you can afford such hedonic products. And at the same time, if you're a very rich country, you're likely to have a better education system. more funds for research facilities and so on, and that thus you produce more Nobel laureates. But you can take that a bit as humorous, like here Eric Cornell, who said, I attribute essentially all my success to the very large amount of chocolate that I consume. So he doesn't look like that though. Yeah. Okay, the second step is then going to the details, meaning finding adequate indicators for each of the constructs that you attempt to measure. And we refer to these as indicators or items or manifest variables. Manifest because, well, the construct which is latent manifests itself in these variables. This is actually the most challenging step, at least my opinion, because you have to find a clear definition of the construct and actually find measures which correspond to this definition. It's oftentimes underrated, but it's very easy to produce like a mismatch between what you think you're measuring and which items you're actually using to measure this. Yeah, so that's why we have to be really careful in conceptualizing the latent variable. So what is it really that we are looking at? So what is corporate reputation in our example? Is it like a personality trait of a company? I might now say, well, no, yeah, but there's actually quite a bit of research that uses like personality descriptions for companies to infer on the underlying reputation. There are also more like trust-based approaches to do that. However, the approach that we draw on with the competence and likability is actually a social expectations approach. So people have expectations towards company, for example, that does not pollute the environment, produces sustainable products, treats its employees well, and so on. And these expectations can be met, or companies can fall short of these expectations. If they meet them or exceed them, then people would ascribe a high reputation to these companies. See, and what I just did here is simply rationalizing the idea of what reputation actually is. People have expectations, social expectations, not only when it comes to product quality and prices, but also like a general behavior of a company. And then they actually measure or compare the performance of the company with these expectations that they formulated. You then have to identify a set of relevant indicators and also decide what the relationship between construct and indicators is, which is obviously related to each other, right? You would use different set of indicators for, say, a formative measurement model than you would use for a reflective measurement model. You see such an example here in this slide where I just took out 3 of the constructs of the larger model that you saw a second ago. Yeah, so here you see a series of statements from surveys where people could agree or disagree to these statements. And again, there's no need to use survey data. Typically, this is done because structural equation models have been formulated in the psychometric tradition. Psychometrics meaning the science of measuring these unobservable concepts, strongly tied to psychology, for example. So what is, for example, depression, right? So you could use a survey to find out about that, but you can also look into behavior to get like an adequate measure of, say, depression. So you could use observable characteristics through which you infer on the underlying concept, or you can use survey data, or you can use whatever database you're having, like also browsing data, which is also behavioral data at the end of the day, web browsing data, for example. But again, typically survey data is being used. And the good news is if you look for corresponding measures that you want to use in these types of models, you can draw on a large array of different articles which document them. Like for example, here, we just pick really randomly some paper from the Journal of Business Research, which is a well-known journal in our field. And here the authors are actually looking into anxiety, and they document the measurement scales. So the measurement scale is simply a compilation of indicators to measure a construct. So they document these measurement scales in a separate table, sometimes in the appendix, where they give the actual statements that they're using, or at least they tell, okay, we drew on the established scale from whoever, right? So it's a good idea to draw on these established scales, but obviously you would adjust them to the context of your study. There's lots of discussion how much adjustment is actually okay. Obviously, some adjustment is always needed, because these scales have been discussed and designed in a different context, in a different country. At least you need to translate them, right? But how much adjustment is okay? Yeah, that's a question which I can't answer here, but my feeling is, looking at these things as from a reviewer's perspective, people oftentimes really change the nature of the measurement, which is not a good thing. So you should change as little as possible. You can also draw on compilations of these scales, such as this one here in the marketing field, Marketing Scales Handbook. But there are very many of these documentations from different fields, such as information systems, strategic management, and so on. So in this Marketing Scales Handbook, you have compilation of a great number of scales with scale descriptions, the origin, some information on its reliability and validity, and then the scale items down here. One thing that I already talked about very briefly is the distinction between reflective and formative measures. So reflective measures, again, means that the indicators are conceived as reflections of the underlying construct. Construct kind of causes the correlation among the indicators, which we then interpret to infer on the underlying construct. However, back in the 60s, researchers argued that not all concepts can be measured like that. Think about, for example, the socio-economic status of respondents. So what defines people's status in a society? Well, you can think about different elements, such as education, job, prestige, maybe income, the house that you're having, the boat that you're having, the beautiful husband or wife that you're having, whatever, just making things up. But you see, you don't have these things because you have a high socioeconomic status. So they're not reflections of something that you have, but they're the reasons why you have this. So because you have this beautiful husband and wife, or wife, and because you have this beautiful house and this very important job, people look at you and say, this is somebody with a high prestige, right? So the question whether to measure concepts reflectively or formatively has triggered quite a bit of controversy over the years, actually starting from 2001 in the information systems world and then also in marketing. So there's lots of controversy here, but still mainstay of research is this one at the left-hand side, the reflective specification, where you see, okay, indicators are the reflections of the underlying construct. Third step is to collect the data and examine it. As I mentioned before, this involves getting rid of outliers or leaving them in, depends on how you define it, getting rid of respondents with suspicious response patterns. So for example, people that just rush through the survey and click like a 7 everywhere, and also treat missing values. One of the key decision factors for you at this stage is already the sample size. So you already know which type of approach you'll be using to estimate this model, and then you have to decide, okay, how many observations do I actually need? Do I need to collect more data? And to make this decision, you can draw upon such tables like this here, power table, which gives you the required sample size for different model complexities, given a certain expected effect size, statistical power, and a significance level. You can also estimate the statistical power of models right away using like R packages, so programming language R, and use this as a means to estimate the statistical power of your analysis. So in this case, for example, you would look into the most complex regression in our model, which is equivalent to looking at the maximum number of arrowheads pointing to a construct. So for example, in this model up here, you would see the most complex regression occurring here for quality, where there are actually 8 indicators pointing to this construct. So this is the most complex regression. And we would then have to decide, okay, what is the significance level that we assume? Typically 5%. We'd have to say, what's the statistical power that we assume? Meaning, what is the share or the probability that we can actually identify an effect as significant, given that it's actually prevalent in the population. And the standard percentage here is 80%. And then we'd have to make an educated guess as to how strong the effects actually are. Stronger effects are easier to trace, obviously. So for example, if we assume like an intermediate to lower effect size with this model up here, 8 arrowheads point to a construct, and assuming 80% power and a 5% significance level, we would actually need 81 observations to estimate this model up here, which might be a bit surprising to you given the complexity of the model. But this rule of thumb that I just came up with here is actually related to partial least squares. Yeah, partial least squares estimates this model not as a whole, but partially, as the name already implies, which has some consequences for the optimization criteria that we are assuming here. But primarily, it's also an advantage because you can draw on much fewer observations to estimate this type of model. We're actually already in the middle of the discussion of how to estimate this model, and there are broadly 2 approaches that we can distinguish here. Both actually originate from Herman Wold, a Swedish econometrician who worked on time series modeling and late in his career on the causal interpretation of multiple equation models. And he had 2 doctoral students, Carl Jøreskoog and Jan Bernd Lohmøller, who actually originated 2 approaches which are very popular as of today. Literal, which stands for linear structural relations, which is also referred to as kind of the covariance-based structural equation modeling type. And then we have PLS, which stands for partial least squares, which is what we call a composite-based approach to SEM. Composite-based because this approach actually computes scores for the latent variables in the form of composites, which are linear combinations of the indicators. So actually Herman Wold very much believed in these 2 approaches, but he was actually more in favor of PLS, one can say, because PLS actually follows more like an econometric tradition where you would conceive these measures as kind of proxies of the underlying concepts. So they are explicitly considered as approximations. While you may see this actually as a disadvantage, it's probably a bit more of a realistic view of measurement because any measurement that you use, no matter how perfect it is given some statistic, is very likely only an approximation of the truth, right? So if I give you a survey asking you for your satisfaction with this lecture here, I don't think I really have the notion that I would get a perfect measurement out of this. Yeah, so what the best I can do is get an approximation. And this is also what Herman Wold was thinking about. Yeah, so think about measurement as an approximation, because on the other hand, yeah, so this is, you might see this as a disadvantage, but the upside of doing this is that you use suddenly an estimator which can handle much bigger complexities in terms of models. So PLS can handle much more complex models compared to the literal approach. This is actually one of the key distinguishing features between the 2, model complexities. Yeah, PLS, because it estimates partial model structures, can estimate models which with many more parameters than you actually have observations. This is not the case in covariance-based SEM, where you quickly reach limits, meaning that if you have a reasonable small model, I would say, like with 4 to 5 constructs, you need about 200 up to 400 observations, depending on the data structure, to actually get a result. And then the question is, how much statistical power do you have? Typically at these sample sizes, covariance-based SEM lags behind PLS. So if you're interested in statistical power, PLS is actually the method you would use. PLS doesn't make any distributional assumptions compared to the other approach for estimating structural equation models. So it's a non-parametric method. That's actually not a very strong argument for using PLS in my point of view, because covariance-based SEM is reasonably robust against distributional assumption violations, particularly when the sample size is high. Plus you have numerous newer estimators which can actually handle non-normal data quite well. Yeah. But fact is, these estimators actually require higher sample size again, so that's obviously a disadvantage. So 2 more important features of the 2 methods that are worth discussing are that covariance-based SEM actually has a clear criterion that's being optimized. Yeah, so what covariance-based SEM does is actually trying to minimize the divergence between the empirical covariance matrix, so the one that we observe, and the model implied covariance matrix. So the covariance matrix that you would be getting if you use this model and assume that this model was actually correct. Yeah, so this divergence is supposed to be minimized. And with this optimization criterion at hand, you can also make a statement about the goodness or fit of a solution. So you can say, okay, given the divergence that I observe, I believe this is a good or a bad model. Yeah, this is not possible in PLS. Well, it's not possible, I wouldn't say that. There are goodness of fit measures, which, however, do not perform very well. At least the simulation studies that I saw thus far paint a rather pessimistic picture, I would say. Yeah, but I mean, obviously you could use a similar approach in PLS. But the problem here is that this divergence between the two covariance matrices, which you can also compute, right, is not explicitly being minimized in PLS. It's more like a side product of the analysis, because what PLS actually does is looking into the variances, not the covariances. So it's very much focusing or following an econometric tradition, meaning that it tries to maximize the R-square of the dependent variables, the dependent constructs, and also the kind of the R-square, the explained variance of the corresponding indicators. So rather than looking into model fit, PLS is more concerned about prediction, actually, telling us whether we can use the estimates to predict new or unseen data. A bit of a philosophical distinction also lies in the measurement. In covariance-based SEM, the constructs are being conceived as factors. Factors don't have any scores. So actually you can estimate the model without knowing any of the construct scores. They are unknown. And actually you can assign scores to them, but there's an infinite number of different score sets that you can come up with, which generate the same types of results. It's largely overlooked. In some of our research, we actually show that this is quite problematic. And in PLS, however, you have explicit scores for these constructs. So you get linear combinations of indicators to come up with composite scores, which are seen then as proxies of the underlying concepts. So this is something that has been viewed pretty critical by some researchers who say, well, representing latent concepts with composites is simply not possible. But other than just hearing it's not possible, I never got any reasonable argument why this is not possible. Yeah, so why can't I conceive a construct as a linear combination of indicators? If I ask you, are you satisfied with this course? And please give me some indicators that you would consider. You would probably think about the satisfaction in terms of different elements that constitute your satisfaction. Yeah, so for example, me, the lecturer, the slides, the pace of my presentation, and so on. Yeah, so you would use these as indicators, and jointly they kind of generate your perception of this lecture and constitute your satisfaction. So given that, why is it not possible to measure satisfaction as a composite of several components, right, or several elements? I don't know. And if you talk to psychometricians about that, they don't have a compelling answer either. Yeah. So this is subject to big discussion. Yeah, and basically the primary philosophical distinguishing features between the two methods. Yeah, because if you have heard about some discussions, is PLS a good method or not? It basically boils down to this. Yeah, it's using composites to represent unobservable variables, and the others use factors. Factors have commonly been used. Now you have composites. Well, use the other or the one. Well, I can't give you a reason why you shouldn't use composites. Yeah, and as I said, I haven't heard any good reasons why you shouldn't be doing it. When it comes then to the model assessment, we look into different type of criteria, and this is where I would spend now a great deal of time if I had more time. Yeah, namely the model assessment. Model assessment follows a stepwise process where in reflective measurement models, we would first look into what we call the internal consistency reliability, meaning that we would look into the correlation patterns of these indicators associated with a certain construct and see whether these are actually high enough. It's a bit more complicated than that, but the question is the set of indicators actually reliably measuring the underlying construct? And we would interpret each of the indicator as like a separate little test of the underlying construct. So looking into the correlation patterns then gives us an indication about reliability, both on the indicator and a construct level. And we also look into convergent validity, meaning are the relationships between construct and indicator strong enough? So does the construct converge in its indicators? Finally, the most important element here is actually the discriminant validity assessment, meaning that two constructs which we believe are conceptually distinct should also be empirically distinct. In the most extreme case, we would observe a unit correlation between two constructs. That would be a bit problematic because if we put them into the model as separate entities, but they're actually perfectly correlated, our decision was obviously wrong. And with this wrongness of the decision, we would run into problems when estimating the relationships of these two constructs with any other construct in the model. So discriminant validity is the central element of reflective measurement model assessment. Because of the way we actually specify the relationship between constructs and indicators, these criteria for reflective measurement model assessment are not applicable to the formative case. The primary reason here is that the indicators are not necessarily highly correlated. Remember, reflective case would say that the construct causes the correlations among the indicators, but in a formative case, the indicators can actually be mutually uncorrelated, but yet they still might be valid measures of the underlying construct, such as socioeconomic status. You might have a great job, have lots of money in the bank, but you don't own a yacht, you don't have a big house, you don't have a fancy car because you're just not using it. But so what I want to say here is that these indicators, like having a lot of money in the bank and having a big house, can be correlated, but there's no need for them to be highly correlated. So this is why we need to look into a different set of measures, which you can actually see here on the screen. So the essential element that we are actually looking at is reliability and validity. And reliability basically means, do the indicators, which are represented here as like shots at a target, actually measure the same thing? Are they closely condensed around a certain area? And if they do, meaning they're highly correlated, we can believe or we can interpret the measure as reliable. This is, for example, the case here at the left-hand side and second from left, where we have reliable measurements. The red dots, the indicators or shots at the target are very close to each other. The green dot tells us whether the measurement is actually on average hitting the bullseye. And you can see this is the case here. We have a valid and reliable measurement. In this case, however, the measurement is reliable but invalid. We also have different cases here. One telling us that reliability is actually a necessary condition for validity. If a measurement is not reliable, it cannot be valid. So I don't have too much time left, but there's just one thing that I want to discuss in like a fairly bit more detail. Give me 3 minutes, maybe. A part of the structural model assessment. So I'm not going into detail regarding these analyses here, but there's one thing I want to distinguish here. It's the distinction between explanatory power and predictive power. So this is a central element of structural model assessment. Explanatory power means that we try to explain the data that we used for model estimation, giving the estimates that we generated. So whenever you run regression, you get an R-square. The R-square tells us how good of a job is my model doing explaining the dependent variable, given the data that we just used for model estimation. This is not prediction. Prediction means that we use the model estimates, use new data as input for the independent variables, and then use this combination to predict the outcome. So we have estimates, we combine them with information that we have regarding new observations, and then we predict the outcome of new observations. People often confuse these two. And to showcase this, Let me illustrate this here using a recently published paper of ours, where we actually look critically on the model evaluation practices in human resource management. So it's a bigger story behind that, but one element of the paper is actually a replication of a well-known model on job satisfaction in aging workforces. So we took this model, published in 2015, we used new data, and then we ran a set of analyses. So for example, what we did, we drew two samples, so-called training and a holdout sample. The training sample is actually being used to estimate the models. Yeah, so we use this data that we have to estimate our, in this case, simple regression parameters. So it doesn't matter whether we're using PLS, structure equation modeling, or anything else, it's the same logic, right? So we use the training data to estimate the model, and then use the estimates that we are generating to predict the holdout sample. Yeah, so the 250 observations were left out, yeah, and these are the ones that we want to predict. But we didn't do that once. We did that 1,000 times. So we took the data set and randomly took out 250 observations, estimated the model with the remaining observations, predicted the head-out observations, and then repeated this over and over again, each time drawing a different holdout sample. So the idea was to contrast the results in terms of explanatory and predictive power. And this is what we get here. On the x-axis, you see the explanatory power as described by the R squared. The R squared tells us, given the model estimates, how well of a job are we doing in explaining the dependent variable of our training sample. The RMSE, root mean squared error of prediction, tells us the degree of predictive error that we are generating with these estimates. So we're using the estimates to predict the holdout sample. So what you see here is a positive relationship between R squared and predictive power. So the higher the R squared, the higher the predictive power. Well, that's a good thing, right? But the problem is the variation is immense, right? So you can see lots of dispersion here. For a certain level of R squared, you see vastly different levels of RMSE values, meaning, yep, there is a positive relationship between explanatory and predictive power, but for a certain level of explanatory power, you can do very well in terms of prediction or perform very badly in terms of prediction. This is what we did here, but just by taking out like a small fraction, and we took this out because the original model's R squared was 0.44, something like this. Yeah, so we took this average R square out, said, okay, around this average R square, how high is the level of predictive power? And you can see this on the density plot here. Yeah, so for this range of R square values, we get a vast range of different RMSE values. Yeah, and that's very bad news, because even if you have a certain R square which you perceive as satisfactory, that does not mean that the same model actually performs very well in terms of prediction. Yeah, so focusing on explanation is great. Yeah, but its main reason why you're doing this should be to identify model overfit. If you're getting a very high R square for a certain model which looks into behavioral aspects, then you should be very cautious, meaning that, okay, maybe this is more a case of model overfit. Yeah, so you're actually tailoring the data too strongly, or the model too strongly to the actual data that you're having. That doesn't tell you whether the model is actually predicting anything well. So with that being said, exactly 1 hour. Damn, that's a good timing, right? Here's some outlook on introductory literature, which you might want to look into. We wrote a primer on partial least squares, which has just been published in 3rd edition, where we use this using easy to apply statistical software. We also have an R adoption, which is more like a workbook. But the nice thing about this, you can actually download it for free. So it's an open access book published with Springer. So you can just go to https://tinyurl.com UBB -PLS and download your copy free of charge. Right? So if you want to take a look at this and see, okay, is it something for me? Then this would be a resource to look for. A nice paper which gives you an overview is this one here, actually co-authored with a researcher from your university, Radomir. I'm probably saying that wrong now. Sorry about that if you're listening. Been published in Psych and Marketing. It's like an overview article of use of PLS in the marketing discipline, and gives a nice insight actually on common mistakes and future developments. In terms of future developments, what I've shown here is like really the basic stuff only. Obviously, there's many more that you can do. Look into unobserved heterogeneity, extract latent classes, compare different groups of data, predict different observations in different model configurations and compare these model configurations. Also looking into more complex modeling options like mediation, moderation, mediated moderation models, moderated mediation models, higher order constructs, non-linear effects, endogeneity, you name it. So there are many, many things that you can actually do here. And we document some of these actually in our advanced issues in partial least squares. So with that being said, thank you very much for your attention. And now I'm very much looking forward to any questions that you might have. Thank you very much.
So thank you also very much for your informative and entertaining presentation. So I would like to ask you two questions. And the first one is related to the fact that some scholars say that PLS as a data analysis method is not highly regarded by top journals in social sciences, including business and economics. How would you comment on this?
Nice one. Yeah, that's actually a myth. Yeah. PLS is a full-fledged structural equation modeling estimator, which has gained vast prominence in a variety of fields. So we see PLS application in top-tier journals, including like the Journal of Marketing, actually Nature journals. Recently saw a paper published in PLOS One. Yeah, so it extends to many different fields in journals with extremely high impact factors. Yeah, so there are critics of the method which claim that it's not well established conceptually. There's no statistical underpinning of the approach. Honestly, I have no idea where this comes from. It's kind of an urban legend that's being spread. There are countless articles highlighting the statistical properties of the method, and researchers draw upon these articles to publish PLS research in top-tier journals. Yeah, so this is not a problem at all. Having said that, there are some editors who polarize the debate. So we've seen editors seeing PLS applications very critically, saying that they're practically rejecting all PLS manuscripts. Yeah, happens. But there are these dogmatic viewpoints also regarding theories or entire research fields. So this is nothing where PLS is particularly exposed, I would say.
Okay, yes, I understand. So, and is this method appropriate also for the analysis of secondary data, the data that are not collected directly?
Yeah. The problematic aspect of secondary data is that it actually is not following the idealistic principles of measurement theory. So you're using lots of indicators from secondary data source, which have been collected for a different purpose. But this purpose means that it's not following the strict requirements of, say, reliability and validity assessments. This would be a problem in other structural equation modeling estimators, which have pretty harsh requirements when it comes to this. PLS is, say, a bit more forgiving when it comes to processing these variables. Doesn't mean that you should do it, but at least you can, and you can assess whether the quality is sufficient to warrant its use in this specific case.
Mm-hmm. Okay, good. Thank you very much again, and see you next week in Cluj.
Yeah, I'm very much looking forward to it. Yeah. So thank you for your attention, everyone.
Thank you very much.
Yeah. Take care.
Take care. Vă mulțumim și dumneavoastră, dragi membri ai comunității UBB, și vă așteptăm în viitor la conferințele organizate de Institutul STAR.